Welcome back. Here is another unusual example. Unusual because you will see the operation is not rather commonly used. Consider the set of all 2 by 1 column matrices with real entries. That is, let V be the set of those column matrices 2 by 1 where the entries are real numbers. Okay. Let us define vector addition as vector AB O plus vector CD is the vector given by A minus C B minus D. Let us define scalar multiplication as R O dot vector AB to be RA RB, where R is any real number and vector AB is any that symbol means belongs to V. So any vector from the set V. What is unusual here? Notice the O plus is actually A minus C, B minus D. So let's see whether this O plus and this O dot, that is the vector addition and the scalar multiplication results in a vector space. So by design we have closure in both these operations. What does that mean? If I take a vector from this set, vector from this set, if I apply O plus, do I land with a vector in this set? Well, A and C are real numbers, so A minus C is a real number. B and D are real numbers, so B minus D is a real number. So indeed, this vector lands here because you want real numbers as entries. Likewise, when I apply the O dot operation, R is a real number, A is a real number, so RA is a real number, RB is a real number, so this vector lands back in this particular set V. So you have closure. Now let us check for other properties. What about commutativity of vector addition? Is that the case? So let's check. Left hand side, vector AB O plus vector CD gives us A minus C and B minus D. Okay, vector A minus C and B minus D. On the right hand side, vector CD O plus vector AB gives us C minus A, D minus B. Now, A minus C usually is not equal C minus A. B minus D is usually not equals D minus B. When? Well, when you say something is not, then you have to provide an example. Suppose A is 3, C is 1, then A minus C is 2, whereas C minus A is negative 2. Likewise, when B is 5, D is 7, B minus D is negative 2, D minus B is 2. So they are not equal. So if it fails, if you say something is not, all you have to do is one counter example. And you give counter example, which means this equality does not hold true. That is, the vector addition is not commutative. In other words, I don't even have to check rest of the properties. My given set with those given operations, O plus and O dot, does not form a vector space. So how do we define O plus and O dot so that we do obtain a vector space? So start with the same set, 2 by 1 vectors, columns, that is with entries from the real numbers. Define vector addition O plus. Vector AB O plus vector CD is A plus C and B plus D. The vector A plus C, B plus D. Define scalar multiplication. Take a real number O dot vector AB, RA, RB. For any real number R and any vector AB. By design, we have closure. Just as I explained before, you see the entries are real numbers. The size is appropriate, 2 by 1. So this will land back in the set. This will land back in the set. Now let us check other properties. Is the commutativity True. Vector AB O plus vector CD is vector A plus C B plus D. Notice this addition is within real numbers. So addition is commutative among real numbers. So I can change the order C plus A, D plus B, which in turn tells me it's vector CD O plus vector AB. What about associativity? Is O plus associative? Well, consider vector AB O plus within parenthesis vector CD O plus vector EF. That is, I'm going to vector add these two first. That's what the parenthesis means. You have vector AB O plus vector C plus E D plus F. Now, what does O plus do? Add A to the first entry, add B to the second entry. So you see, first entry and second entry have been kept in parentheses. You are adding A later, B later. Now parentheses can move A plus C plus E, B plus D plus F. Now you are able to split this across O plus EF. Okay. Vector A plus C, vector B plus D is in turn vector AB O plus vector CD. Then a later vector O plus vector EF. In other words, notice the parenthesis, initial parenthesis move to the left. So O plus is indeed associative. What about additive identity? So notice we are going through every single property required to be a vector space. So there is an additive identity, that is the vector 0, 0. Vector AB O plus vector 0, 0 is vector AB. On the other hand, 0, 0 vector O plus vector AB is also AB. So notice, I just need to check one way. The other way automatically holds if you are commutative. Okay. What about additive inverse? Given any vector AB, is there its negative? Well, it does. The vector with negative A, negative B, if I O plus add to vector AB, I get 0, 0. 0, 0 was our additive in identity. Okay. Again, by commutativity, I don't need to check this, but I can always check. Distribution. So you see, there are, in addition to closure, there are 4 O plus properties and 4 O dot properties. The 4 O plus properties are commutative, associative, existence of additive identity, existence of additive inverse. So these 4 in addition to the closure. Now there are 4 O dot properties. The first one is O dot is distributive over O plus. Okay. That means scalar multiplication is distributive over vector addition. So that tells you I should have 2 vectors because I'm going to use vector addition, and 1 scalar. So take any R real number and any 2 vectors from your set V. Then R O dot, add the 2 vectors, vector addition AB and CD. That gives you vector A plus C, B plus D. Now if I apply O dot, that is R times in parenthesis A plus C, R times parenthesis B plus D. Well, this multiplication is within real numbers. So multiplication distributes over addition. So that gives you RA plus RC, RB plus RD. Now, along these pluses, I can split my vector into vector added, vector sum of 2 vectors, RA, RB, RC, RD. R comes out via O dot. Likewise here, R comes out via O dot. In other words, O dot is distributed over O plus. Now what about the other distribution? O dot distributive over addition, not the O plus, regular addition among real numbers. So I'm going to add 2 real numbers. So I need 2 reals and 1 vector. Okay. 2 reals, I add them. oh, that should be an O dot, not just a dot. It should be an O dot because that's a scalar multiplication to vector AB. That gets us R plus R plus SA, R plus SB. Now this is multiplication among real numbers. So A distributes to R and S, likewise B distributes to R and S. Now you are able to split here via vector addition and then split out the R and S via O dots. Okay, so one error, that should be an O dot because that should be a scalar multiple. One scalar, one vector. Okay, which tells you O dot is distributive over plus. You see, that got distributed. Now, is O dot associative? O dot associative, that is scalar multiplication associative. So you see, if you have two vectors, we don't know to multiply, we only know to add two vectors in this set because that's all given to you, O plus. So multiplication associative means you need two reals, okay, because that you know how to multiply. RS in reals and AB among vector, from the vector. So let's see this. Multiply RS within the real numbers, then O dot with vector AB, then RS goes to A, RS goes to B, there. Now among real numbers, multiplication is associative, so that is RSA. Likewise, let me move my cursor so you'll be able to see this. The parenthesis moves because of associativity among real numbers, and then using O dot you got the R out, and then using O dot you got the S out. So O dot is associative. What about multiplicative identity? Well, for 1 in R, that is real numbers, 1 is an element of a set of real numbers. 1 O dot vector AB is 1A, 1B, which is AB. So that 1 from the reals is the multiplicative identity for O dot as well. So you see O dot satisfied these four conditions, 1, 2, 3 and 4. So these four conditions are in addition to the closure. So you need first closure and then 4 properties of vector addition and 4 properties of scalar multiplication to fetch a vector space. So in all 10 things, closure for each, then 4 additional properties. In all 10 properties we have to check, and we did check. So you have a vector space. Let's continue in the next video.